This is a quick summary of some of Section 2.1 concepts. I'm going to start with this slide that I posted to Lumen, and this reflects one step of our statistical inference process, the step about creating a simulated distribution using Rossmann chance. There's two ways we can do that. If we have a categorical variable, we use the one variable with sampling. We use the one variable with sampling. If it's quantitative, we use the one proportion if it's categorical. When we create a simulated distribution, we use a set of assumptions. The first assumption we use is that the population parameter or the claim is true. This maps to the null hypothesis. H sub 0 is going to be equal to mu, or it's going to be equal to pi. If it's equal to mu, that is if we have quantitative data. And if it's equal to pi, we have categorical data. When we have categorical data, the assumptions or describing the process, this maps to our assumptions. These are the things that we're going to instruct the computer to use to generate our simulated distribution. One, in the probability of heads entry, we always put the pi value or the claim. Goes here and we enter it as a decimal. In the second entry, we put our sample size n. And then in the number of repetitions, we either put 100 or 1,000. We just repeat this a number of times so that it will generate a distribution of simulated p-hats. The p-hats are generated assuming I have a sample size, whatever I entered up here, and the numerator will give me the number of successes, assuming that pi is true. We'll just focus on categorical data here. We would do something similar if we had quantitative data. So when we generate the distribution of sample statistics for categorical data, the computer is generating a simulated p-hat. All right, however many repetitions we tell it, 100, 1,000 or more, the computer is going to generate that number of p-hats. Those p-hats are going to have the quality that we would have number of successes out of whatever our sample size is that we enter into our applet assumptions. And it generates these p-hats assuming that that pi value is true. This relates to our null hypothesis that the parameter or the claim is true. As we repeat this over and over again, as the number of p-hats increases towards infinity, the center of our distribution is going to become closer and closer to this pi value that we enter into the simulated distribution. So each dot represents a simulated sample statistic, a p-hat, that represents the number of success over whatever sample size we put in. The mean or the center of the distribution is going to approach this true value of pi. The more p-hats we generate, the closer this pi gets to, or the center gets to the value of pi. And as we increase those p-hats, or the number of repetitions, this will really approach a normal distribution. As n gets bigger and repetitions get bigger, this will approach a normal distribution. So our statistical inference process follows a set of steps. The first thing we do is that we ask a research question, we write our null hypotheses and our alternative hypotheses, we collect a representative sample, and we observe or we calculate our statistic. That statistics could be mu or pi. Then, based on mu or pi, we create a simulated distribution. This is in our Rossmann chance applet. We do this so that we can compare our observed statistic to what it would look like, assuming that our population parameter is true. Let's look at an example. So in one proportion, there's two ways that we can enter data into the one proportion applet. This part up here, describe the process, always relates to our assumptions. It's what we're telling the computer to use to generate all of our, in this case, p hats. These are all p hats because it's categorical data. So we would say, we would enter here what is pi, we would enter here what is n, and then we would tell it how many p hats to generate or how many repetitions. If we're talking about a proportion of heads or a p hat, we would select proportion of heads, and then we would enter our actual observed p hat in this box. The other way that we can enter data into the one proportion applet is, again, we would put our pi value here, we put our n value here, and our number of repetitions here. We can also enter the number of heads or the number of successes. Remember, there are three pieces to a p hat. The proportion is the number of successes divided by the sample size. In this case, we're entering our observed p hat here. In this case, when we have number of heads selected, that really relates to what our number of success is, and that is what we put in this box here. So if we have any of these three pieces, we can, or two pieces, we can calculate the third piece. Let's take a look at this actual problem here. So we have a spinning a coin, and it says, unlike tossing it, we may not get heads and tails in an equal proportion. So I spin the penny 125 times, and I get 54 out of the 125 times. We want to know if we have significant evidence that the coin lands on heads at a proportion different than 50%. So our null hypothesis in this case would be pi equal to 50%. So this would mean that I would get heads and tails equally. Alternatively, we're saying we want to know if it's something different than 50%, pi not equal to 50%. Here is our hypothesis test. All right, so then when we go to the one proportion applet, we want to always, always, always enter the null hypothesis, the pi value, pi equals 0.5. So that is correct. Then, so we're going to put that in here, 0.5. Then in the applet, it says, what should we enter in the number of tosses? Well, we want to go with exactly what our observed sample was, n equals 125. So that would be 125. And then we would repeat it either 100 or 1,000 times. Then the next question says the simulated distribution of sample statistics will be centered at approximately what value when we click on proportion of success? Well, we have told it we want to generate a distribution assuming that pi is equal to 0.5. So when we generate the distribution, it's going to have a center approximately equal to pi. Okay, so on this prior page here, remember, it's going to approach pi, the pi value at the center. So let me pull Rossmann-Chance up and we can take a look at this. So if I put in 0.5 and I put in 125 tosses and I repeat it 100 times, and I'm going to show my summary statistics, and I draw my sample. So see here, right, I've told it to assume that pi equals 0.5. But when I have 100 repetitions and I generate the simulation, I get a mean or a center of 0.49. Okay, it's close to 0.5, but not exactly equal. If I increase the number of repetitions, to 200, notice how I'm now at 0.497. If I increase it to 300, I'm at 0.498. If I keep increasing this to 800, I'm at 0.499. So the more repetitions that I have, 1,000 repetitions, the center of the distribution or the mean is approaching 0.5 because that's what I told it to assume. So when I'm looking at the distribution of sample statistics, it is always going to approach being centered at whatever I entered up here. So it's always going to approach 0.5. And then this is correct. I have 3 pieces. P hat is equal to the number of successes divided by my sample size. So we have 54 out of 125. When we divide that, that's 0.432. So if I want to find where this center is when I switch to number of heads, I would simply take, right, 125 times 0.5 is equal to 62.5. If this center is at 0.5, I want to multiply it by n to give me approximately what the number of heads would be, or number of successes, which would be 62.5. If I look at the rock, paper, scissors example, we're told that when we played this game a total of 225 times, a person picked paper 63 times out of 225. So that is our p hat. P hat is equal to 63, our number of successes, over 225. So number of success equals 63 in our sample, and n equals 225. And we want to know if we have evidence that the person is in fact not picking paper randomly. Do people actually pick one of the other categories, rock or scissors, more frequently than paper, compared to picking randomly? So if we pick randomly, my long run probability of selecting paper would be 1 out of 3 equals 0.333. This would equal pi. In the long run, if people pick randomly, my pi value is equal to 0.33. So my null hypothesis would be pi equals 0.33. People pick scissors randomly. Not scissors, they pick paper randomly. Alternatively, we want to test, do they pick paper at a different rate? We want to know if pi doesn't equal 0.333. Not random. So when I create my distribution, I want to create what would it look like assuming the null hypothesis is true, assuming that people pick paper randomly. So I would put in here pi equals 0.333. And then, yes, our number of tosses, we're always going to match our actual observed sample size of 0.25. And again, when we simulate this distribution, it's going to be approximately centered at whatever we put here in our assumption. We told it that 0.333, 125, and let's say we repeat it 100 times. It's going to create a bunch of p-hats, and it's approximately going to be centered at actually 0.333 because that's what we told it to. So the center is always going to be approximately equal to our pi value. The more samples that are more repetitions that we create, the closer that the center is going to be to 0.333. If I come here and let me reset this, pi, assuming that people pick paper randomly, 1 out of 3 would be my result. Okay, and then if my sample size is 225 and I repeat that 100 times, I can see here that my mean of the sample or the center is 0.336. It's pretty close to 0.333 because that is what we told the computer to do. If I draw more samples, now I'm at 0.336. 336. Let's keep drawing more samples. 0.335, 0.334, 0.333. The more repetitions as I get closer toward infinity, this mean of the simulation is getting closer and closer to what we told it to be in our assumptions.